So we discussed earlier with the application of finite element method for beam element, right? In the third video, you can check it. And the link will be provided in the description for all three videos, the introduction and the bar element and the example, and then the beam element. This is the fourth video for the example in beam element, right? So yes. So we considered how to derive the stiffness matrix for the beam element, right? In the third video, right? So considering, and for example, we have for the video one for the introduction environment, links are in the description in this video, right? All three videos which has been published earlier, an introduction and to the bar element, and then the bar element example in the second video, and the third video we have for the stiffness derivation and the assembly for beam element, and this video will consider an example of the beam element, right? So yes, we will consider this example, and we don't need these dots. Let's erase this for a while. Let's erase this for a while, and then okay. So this is the example of the beam, right? So you need to solve this using finite element method, right? So you saw using these matrices, right? What you saw was stiffness matrix was there, and you can determine the displacement and then the forces, right? So in this example, right, you need the reaction forces. So that means definitely you should have a node. So that's how you go to this example, right? So that means you definitely need node at here, right? Node at here, right? So, and you need a node at here because you need the reactions at these locations, right? Okay. So you will have reaction and bending moment at fixed end and only vertical reaction at the far end, right? And you remember you have to you have to account for the external loading using your nodes, right? So we will assume self weight is 0. So this point load has to be taken into the consideration of our matrix calculation. So that means you should have a node at that location as well. Otherwise, you can't have that load into the matrix calculation, right? You should, so at least you should have 3 nodes for this element, right, to solve. Okay, so if you call this, so this is your basic example. So this is a 3 noded element. So I'll call this. So I'll call this the displacement b1 and theta 1. Okay, so we know v1 and theta 1 are 0. For the moment we will consider v2 theta 2 because of fixed end. v1 and v1 and theta 1 are 0. Okay, so here v3 and theta 3. So since v1 and theta 2 are 0, so that means the displacements are restricted. So that means that should have a force. So corresponds to F1 and M1. So here you can have F2 and M2. I'll explain this, what is F1 and M2. So these are external loads, right? So you don't have any external load. Actually here you have some external load. I'll show you how to take this into account. So here F3 and M3, right? So this order is very important. V1 theta 1, V2 theta 2, V3 theta 3, and same as F1 M1, F2 M2, and F3 N3. This corresponds to F1, this corresponds to M1, this corresponds to F2, this corresponds to M2, this corresponds to F3, this corresponds to M3, right? So we need to define the element stiffness matrix for each element and then assemble it. And we will do this example using Excel, because everyone is not fluent with computer programming. For instance, me, even I don't uh, I'm not really fluent in computer programming, so I'll use Excel. Okay, so this 1.5 distance uh, is not related to this example, so you can just forget about for now. Okay, I'll use this in the second example. Okay, so you can have, so 3 is given. Okay, 210 gigapascal. I is given, the length is given, total length, right? So we'll go to Excel. And here you have, okay, so I have defined the nodes at here, at the load location, loading location, and the end where I need to determine the displacement and the forces. So okay, so my E is, the Young's modulus is 210 gigapascal, and I is for this value, and L is, so for this is for one element. Okay, one element, right? This is for one element, so I'm basically considering two elements, each is 3 meters. Okay, it is 3 meters, so that means you will have same stiffness matrix for each element, right? Length is same, and the E is same, I is same, right? And that needs not to be same length. If you want, if your load is at something here, you can define a load node at that point. So that means this length and this length need not to be equal. You can still derive the stiffness equation for those two elements, right? So you remember the stiffness matrix had some constant alongside with the matrix EI over L cube, right? So I'm calculating EI over L cube, so that E is 210 into 10 to the power 9, because gigapascal, and I'm considering everything Newton and meter. Okay, so this is EI over L cube, L to the power 3. Okay, so this is the value, and this is the stiffness matrix. Okay, you remember. So this is a stiffness matrix. So once you take EI over L cube out, you can define this matrix. Okay, so you can see this matrix: 2L 6L minus 2L 6L, 2L squared minus 6L. Okay, so then you can evaluate this matrix. Since you know this value, you can multiply this by each value. This value into 2L, this value into 6L. L is given here. Okay, okay, everything is given here. So here you can see this value into EI over L squared. Okay, this value into 6 into L, right? So this minus 2L into this value. Okay, for instance, this value. So 4 into L squared into this value, 4 L into this value, right? So that's basically how you, so here you have the element stiffness matrix with the value, right? Okay, so with the value you have this. If you want, you can take again 10 to the power 8 out and write this matrix. There's no need of that. If you want, you can write that. That doesn't matter because we are solving it using MS Excel. Okay, so my second element also will be like this, right? Because the same length, same E and same I. So you remember how I assemble those matrices? Do you remember? So if your element is like this, right? So from the common node, you have to assemble it, right? Okay. So if you didn't know, please watch video 3 that explains you everything how to assemble that. Okay. So I'm going to assemble it, and when you assemble it, you know you have here the v1 and theta 1. Okay, v1 and theta 1. Okay, and then you have v2 and theta 2 and v2 theta 3, right? Then theta 1. Okay, so okay, this is for the matrix. This is the stiffness matrix. This is the displacement matrix. So basically this gives you the matrix K, right? F equals, this is the displacement matrix. Okay, the same things have been written because to identify the rows and columns. Okay, this is F matrix, right? So F is equal to A times D, right? F is KD, force is stiffness into displacement. So this will be your first element stiffness matrix, and you have to add the second stiffness element matrix by overlapping the common coordinate, right? The common coordinate is v2 theta 2, right? The second coordinate, remember? So you have to add these two like that. So in the third video, I have explained how to add that, right? So first you need to keep everything 0. And for instance, this is v1 row, v1 column, right? So v1 row, v1 column means this will be okay. For the I'll show you how to get that. So if you need v1 v1 v2, so you should get v1 and v2 column, and when it crosses you have this, right? When it crosses you have this value. Okay, so that is there, right? So likewise v1 is not in the second element, so the second element, this is first element is stiffness matrix. Okay, this is how you assemble it. I'm summarizing it again. So for instance, if you take V2 and V2, so there is also V2 and there is also V2 and V2. There is also V2 and V2, right? So you can see when it crosses, you have this value and this value. So that means you have to add those values here, right? You can see you have to add this value. That's it, right? So for instance, theta 2 and V2, V2 rho, theta 2, V2 rho, theta 2. You can see it's negative 500, negative something and plus something. So when you add it, it will be 0, right? Other things, if you're not, so V1, V3 is not in any matrix, right? V1 is, because V1, V3 are not connected within an element, right? So they will be 0. That's why I told you, place zeros at each position first and then evaluate each coordinate, each row and column, right? And this will basically this matrix plus the second matrix, right? So these four will be added together when you form in the global stiffness matrix, right? So this plus this 7 something, so this plus this 0, this plus this 0, this plus this going to be 2 2 4, right? So that's done. Okay, so then v1 v2 is it, so that into displacement, so the displacement will be like this, right? So we know actually this is f1 m1 f2 m2 f3 m3, right? So these are the values you need, right, to determine. Right? So these are the forces you need to solve, and these are the displacement you need to solve, right? This is just, this red color is, don't confuse, it's not a matrix. That's how I mark the rows and columns of this stiffness matrix. Okay, this is the matrix. Okay. This is the matrix. So we actually know that V1. So we know at first coordinate, right here first, F1. So it's restricted, right? So there's a reaction F1 and M1 as well. But V1, the vertical displacement, and theta, it's a fixed support, are 0, right? These two 0. At second coordinate, V2 and theta 2 are not 0. There will be a displacement and the rotation as well. But the external loading, so there's no reaction because support is not there, but external loading is there, right? So you have 10 kilonewtons. So I'll take downward sides positive, okay? Okay. So 10 kilonewton means 10 to the power, sorry, 10 into 1000 newtons, right? And there's no bending moment externally added, right? Okay. So F3, you have it is restrained, right? So you have some reaction, right? F3, and it's a free end. Sorry, it's not a fixed end, right? So you know the bend, it's just a pin end. So you know the bending moment is 0, right? And here theta 2 is not 0, and here V3 is 0 because there's a reaction and it's restrained, so that becomes 0. But there's a theta here because it's allowed to rotate, right? No rotation restricted, no moment generated externally, or uh, no moment generated or not moment given. Okay, so there can be two components. If some loading is here, so that loading can be added to this, right? So keep the So the total force at that location will be given. You have to determine what will be the reaction. Okay. Here, no loads at that point, so that force will directly give you the reaction, right? So here is how to solve this. If some displacement is 0, right? For instance, V1, so you can cut those. You can cut those rows and columns. Here's how you do it. V1 and V. So this V1 is 0. So you have to erase V1 row and V1 column. Okay. And theta 1 is also 0. So you have to cut theta 1 row and theta 1 column, right? And V3 is 0. So V3 is cut and V3 column is also cut. So you have to cut it. Okay. So the remaining will be like this. 10,000, 0 and 0. So this part will be there. And this part will be there. And this part is here. This part is here. So this is our reduced equation, right? This is our reduced equation. Okay. So we can determine what is V2 theta 2. This is actually V2 theta 2 and theta 3, right? Okay. These are non-zero. Okay. So you have an F matrix, you have K matrix, you have to determine this. So what you need to do is multiply this by inverse of this K matrix. So you can write the inverse like this. So here's how to find the inverse, right? So inverse is also 3 by 3 matrix. So you need to select 9 cells and just press equal sign. So that it will be automatically in the first cell of the first row, first column. Then press M in. Then it will show something M inverse. Then select the array. Array means the matrix. So I'm selecting this matrix. Then press Control and Shift together. And with that together, you can press Enter. Control Shift Enter. And that will give you the inverse, right? So you have to then multiply this inverse by this matrix, right? This matrix. So how to multiply that was, this is 3 by 3 matrix, this is 3 by 1 matrix. So solution will be 3 by 1 matrix. So you have to select exactly that solution, 3 by 1 matrix. Then M matrix multiplication. So the first matrix is this, because that matrix multiplication is in order, right? You cannot multiply AB, but it is not same as BA, right? Okay. So then the second matrix, again, Control plus Shift plus Enter. So this is your this is your answer. T1, T2, T3 in millimeters. Meters. This is radian. This is radian. Okay. So you can see there's 0.2 millimeters deflection in 0.2 and theta 1 rotation in clockwise direction. You can see this negative means theta 2 is anti-clockwise, right? So once you plug these, okay, once you plug these, so you can find F1, F2 and F3 because you have already found these values. Okay, I will write it here. Okay, I have now found this one. A2 and okay. Now I need to just multiply these matrices to find this matrix, right? It's already solved, but I will just find that matrix for your convenience. So if you multiply these two matrices, this is the K matrix and D matrix. What we did was, using the known forces, we found the unknown displacement. That's why we need the inverse. Now we know all the displacement. We can just multiply these two, and get the force matrix, right? So I will be getting like this. So for force matrix, like exactly we look like this, right? So I'll call this F1M. So I'll call this a generalized force matrix. So that will be F1M2, then like this. So this is equal to matrix multiplication. Array 1 is this, comma, array 2 is this. Control Shift Enter. So you can see exactly it becomes 10,000, right? So your F1 is it's in the upward direction. So because we took positive, negative in the positive in downward direction. So forces and displacement, same sign convention. If it is downward, force downward force positive, downward displacements are also positive, right? And the clockwise rotations are positive, clockwise moments are positive. Okay, so this force is 6875, so 6,875 newtons. So the bending moment is 11,250 Newton meters. It's in anti-clockwise direction, and that should be, because load is acting this way, it's an anti-clockwise bending moment. And the force 2 we know that's external load, and moment 2 is 0 because we don't have anything, right? Okay, so this is the external, okay, external, not internal. There will be a bending moment, but these are the external forces, external, so at the reactions and the externals, right? So F3 is reaction. Reaction will be there, right? That reaction is 2, 1, 3, 4. If you add this, so even using simple statics, you can verify this. If you add these two values, that is exactly equal to this external load, right? Okay, and this is my 10 to the power minus 12. This is almost 0. Okay, M3 is 0, right? This is 0 actually. So this very small value, because this due to this matrix multiplication. So this is very close. This is almost 0. Okay, bending moment is 0. That should be, because it's a pin end, right? So what happens if you want to know, if you extend this to a 5 node? So you need to determine this and this, right? At these locations, the displacements, right? You need to know. Now you have the displacement, right? So finite elements will give you any of these displacement as a function of these two elements, right? So I'll show you this. So if you had 2, 3 nodes, so if you determine any of these, so any of these displacement at this location will be given as a function of the ends, right? So this will be as a function of this and function of this. This will be a function of this and this, and a function of this, these two, right? This will be a function of these two displacement, right? So when you increase the number of nodes, right, So this, any of these location will be given as function of this and function of this. Any of these location will be given as a function of this displacement, function of this displacement. So this is interpolating between a larger segment, but this is interpolating between a smaller segment. So this is more accurate, right? This is being more accurate. More accurate, right? That's exactly happen when you meshing. So when you mesh it, so your accuracy is getting, so you can define any nodes here. Then these displacements, for instance, this displacement here will be function of this one and this one, because it is closer to these two rather than these two, right? So, but with the, it's now it's a 5-node element, so 2 degrees of freedom, then it will be 10 by 10 matrix. So solving is not easy, but still you can use Microsoft Excel, right? Let's show it. This is how you do it. So since the elements are same, okay, so the node is defined at 1.5 meters, 1.5, this is also 1.5, this is also 1.5. So the exactly same element stiffness matrix for each member. So you show this, you seen that in the earlier one as well, right? Right. So right. So I can define the same matrix. So this is the element matrix 1, and add with element 2, and add with, so this is element matrix 1, right? So you know how to assemble that. So this is element matrix 1, so this is element matrix 2, element stiffness matrix, okay, stiffness matrix. So this is element stiffness matrix 3, so you just need to add it in that order, right? So this is element stiffness, so because there are 4 elements, right? So this will be v1, okay, this will be theta 1, okay. Okay, it is connected at v1 theta 1, and this is connected v2 theta 2, and finally v5 theta 5. The same thing will be there. Right? Be there, right? So this red colors indicate just to notate these matrix elements, right? This is the correct D matrix. So I will show you how to get it, right? So that's his black color, right? So these are the forces. So I'll call this F1, M1, right? So these are the forces. And we know at first coordinate, you have F1 and F2, the same 3-node element you saw earlier. And that means V1 and V2, because it's a fixed support, V1 and V2 are 0. And second node, you have V2 theta 2, but you don't have any reaction or any external loading. So this is 0 and 0. And F3, you have a load external 10,000, right? But you don't have any moment external. So here you have some displacement and rotation. But F4 as well, F4 you don't have any loading, right? And V4 and theta 4 are there, not 0. Okay, but here you have some reaction at 5, 5th node, and bending moment is 0 because of pin support, right? So again we see this is the first node, this is the second node, right? Right. So you can see a first node, you have reaction F1 and M1, but displacements are 0, right? At the second node is you don't have any loading or bending moment externally, but you have some displacement V2 theta 2. And third node, you have some external loading. So I'm getting downward positive forces and displacements, and clockwise positive forces and moments and rotations. And fourth node, you don't have any loading or moment. It's exactly as the second node. So, but you have P4 and theta 4. Fifth node, you have some reaction in F5, but you don't have bending moment because that's 0 pin support, because there's a theta rotation. And V5 is 0 because it can't go in vertical direction. It has a reaction. Okay. So similarly, what I can do is I can solve these. So I told you how to solve it. If it is 0, cut those rows and columns. V1 is 0, so V1 row and V1 column is cut. Theta 1 is 0, so you can cut it. Right. And theta V5 is 0, so you can cut that column and row V5. You can cut those. The remaining will be, you can exactly take. So this part you can take to here, right? And this element. Okay. So this part is exactly like this, right? This is this part, and this part is here. Okay. And this part is here, and this part is here. What's remaining, you combine it as a matrix, right? And you will be remaining with these values. Again, we have to determine what are the unknown displacements, right? So you need to take the inners of this matrix, right? So it will also be a 7 by 7 matrix, right? So I'll choose 7 by 7 cells, and M in inverse. I'll choose the matrix and Control Shift Enter. Press these 3 together. First press Control, and while holding Control, while press Shift, and while holding both of them, press Enter. Right. So this is the F inverse. So F inverse should be multiplied by this matrix, because this is the force matrix. This is the stiffness matrix. This is the stiffness matrix, and this is the D matrix, right? Right. So square bracket for K, because that is not dependent on external loading, right? When you multiply these two, you can determine the displacement, unknown displacements, right? So there will be this kind of matrix 7 into 1 matrix. So you have to select exactly what will be the multiplication of this. This is a 7 by 7. This is a 7 by 1. So your multiplication will be 7 by 1 matrix. So select 7 by 1. M mult. This is the first matrix. This is the second matrix. And Control Shift Enter. So these are your rotation and moments, right? Sorry, displacement and rotation. So you can see theta 4 is anti-clockwise direction, other thetas are clockwise direction, right? Okay. So you can determine now this entire force matrix because you know the values, right? You know the values now, right? You can determine of these values, right? So we determine the displacement. Now we can multiply these two matrices and find the forces. So I will consider this is, so unknown are only 3, but I will again determine everything, right? Okay, it will be this kind of a matrix. So this is 10 by 10 matrix. This is 10 by 1 matrix. 10 by 10 matrix. This is 10 by 1 matrix. So the multiplication will be also 10 by 1 matrix, right? So let's go to M mult. Array 1 is this, comma, array 2 is this. Control Shift N. Okay, is it correct? Oh, sorry, I have, while I have pasted the stiffness matrix, that's become everything 0, right? So this is the stiffness matrix, right? Okay, and this is thousand. Oh, sorry, it's 10,000. Okay, 10,000. I have wrote it as 100,000. That's why. So you can see F1 is again same things are coming, right? So from the earlier equation we got F1 as this, and so you can see our earlier first coordinate is a first coordinate, that's okay. So you can take the same forces and bending moment, but we define an intermediate coordinate and we calculated the force is actually 0 because this is 0, right? Okay, this is 0 actually because there's no loading, because you can see the value is 10 to the power minus 12, right? This is actually 0, right? So okay, this is actually 0, this is 0, this is also 0, 10 to the power minus 12, 10 to the power minus 12, 12, right? So you can see the values, right? Forces at reactions at the first coordinate are same, and you don't have any force, but you have bending moment, it is equal, so this is also 0, right? So you can see you can define whatever the nodes, but come up with the uh, each same answer. But the thing is, accuracy in this method is high because you have several nodes, that several finite points that define the beam, right? So here you have several displacements. If you discretize it using more nodes, your computational will be higher, but you can still use MS Excel because it is a powerful software, right? You don't need finite element software. If you know the concept basics well, you can use MS Excel well, right? So, and earlier, if you know theta 1 and theta 2, right? If you know theta 1 and theta 2, so any of within these displacement will be a function of these four displacements. So that's that theta 1, theta 2, and v1, v2, and v2, v3. Now we have intermediate locations. We know the displacements, right? So there we can write an more accurate expression between these 2 points for the displacement. Using these 2 points and know the displacement, you can interpolate between two. But in here, you interpolate these between these two. Rather than that, this is more accurate. You interpolate between these two for the displacement between any of these points, right? When you more mesh it, it will reach and converge to a particular answer, right? So machine does not mean that will always lead you to a higher state, but it will converge and it should after a particular point, right? Up to that, your accuracy will be higher, and as well as the computational expense will be high, right? So thank you very much.